Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisense and responsible for production and development of Unisense microsensors. In this presentation I will give you an introduction to how our SOLF microsensors are designed and working, which will hopefully familiarize you with them and helping you apply them correctly. The Unisense SOLF microsensor is out of the amperometric microsensor type, also known as Clark type sensors, and an in-depth lecture about the working principles for these sensor types is available on our website. We sell hydrogen sulfide microsensors in two versions with different electrolytes and electrochemistry. The H2S sensor, which we have produced and sold in many years, and the SOLF microsensor, which we have introduced on the market in 2018 and which is superior to the old H2S sensor for most applications. This lecture will focus especially on the SOLF microsensor and its performance. It will cover the following topics: tip design and detecting principle. I will go through the specifications and give some comments to them. I will explain how our needle sensors are built, and at last I will go through a troubleshooting section. This is a photo of a SOLF sensor, and to the right you see a SOLF sensor in action. Details and general theory about Unisense amperometric microsensors are covered in the lecture about Unisense amperometric microsensors, but I will here briefly describe the tip design and working principles of the SOLF sensors. The outer tapered glass casing is equipped with a silicon membrane. The function of the membrane is to make a barrier between the electrochemistry inside the microsensor and the sample. The membrane is permeable to sulfide. If sulfide is present, it diffuses through the membrane to the working electrode. The working electrode surface is positively polarized platinum electrode, which catalyzes oxidation of sulfide to sulfuric acid. The electrons are delivered to the reference electrode where oxygen is reduced. The reference is placed 10 to 15 cm away from the working electrode, but for sake of illustrating the principles, it is included in the schematic drawing of the tip. The current generated is proportional to the concentration of sulfide outside the tip membrane, and as the current is very small, in the picoamp range, a high quality amperemeter is necessary for amplifying such tiny current. The guard electrode is only used for low-range models to oxidize impurities in the electrolyte, which would otherwise react on the working electrode for the purpose of keeping the baseline low. The cavity is filled with an acid aqueous electrolyte, which ensures electrical connection between the electrodes and ensures charge balance. Reduced dissolved sulfur is present in both uncharged and ionic fractions. In alkaline samples, H2S dissociates to become HS- and S-. At neutral pH values, the fractions of H2S and the deprotonated species are about the same size. Below pH 4, close to 100% is protonated, and at pH 10, almost 100% is deprotonated. As a consequence, at pH values higher than 4, the sensor only measures a fraction of the reduced dissolved sulfur, and to calculate the total concentration, the pH of the sample must be known. If the pH is known, it is possible to calculate the total concentration of reduced sulfur using this equation. As seen, the dissociation constants are contained in the equations, and these are both temperature and salinity dependent, and the scientific community do not totally agree on the numbers, so the calculated concentration is subject to some uncertainty. As the measurable fraction decreases with pH increase, the calculation of total concentration of reduced sulfur based on sensor signal lacks precision at high pH values. In gradient systems where pH typically changes with depth, it takes both a sulfide microsensor and a pH microelectrode to calculate the total reduced sulfur concentration profile. I will now turn to the actual performance and specs of the sulfide sensor and give some comments to them. Recall that these specs are only guaranteed with use of a Unisense meter. The limit of detection is stated to be 0.3 micromolar dissolved sulfide. However, the detection limit is strongly influenced by the application in question. By producing the sulfide sensor with a wider tip membrane, The sensors can be made more sensitive with a detection limit down to 3 nanomolar. The lower detection limit will, however, affect the response time and steering sensitivity. Such low range sensors are only available for sensors with chip sizes of more than 100 micrometer. The chip size ranges from 10 to 500 micrometer. We produce them in standard models with 10, 25, 50, 100, 200 and 500 micrometers. We can, however, make them with chips down to 3 to 5 micrometer. Naturally, the smaller the chip is, the more fragile it will be. Larger sensors are made with thick glass walls, making them quite robust for profiling in matrices. Consult our guide for chip selection for more information. We can custom-make the chip design regarding slenderness and modify the sensor body dimensions if requested. The response time is a function of the sulfide diffusion path length into the working electrode and chosen to obtain the best compromise between sensitivity, response time and steering sensitivity. Small sensors are made with shorter response time than largest, but all standard sensors have below 10 seconds response time. Details on response time is found on our website. The oxidation of sulfide on the working electrode surface goes through more steps, and some of these intermediate substances react slowly. Therefore, the 99% response time are significantly longer than the 90% response time. Sulfide sensors can be custom-made with short membranes to shorten the diffusion distance, and thus sulfide sensors can be made very fast, down to 1 to 2 seconds for a 90% response time, but still with a longer 99% response time. The sulfide sensors respond linearly to sulfide concentrations. It will respond linear up to 300 micromolar dissolved sulfide. The limitation of the linear range is determined by the H2S oxidation capacity of the working electrode. Thus, sensors which are produced to measure concentration in the millimolar range must have a reduced sensitivity. This is done by reducing the diameter of the tip membrane. The spatial resolution equals the tip diameter. This is just a rule of thumb because it cannot easily be validated. The sensor will sample sulfide from a very minute diffusion sphere at the membrane/sample interface. But physical disturbances should also be considered, which increase with tip size when profiling in biologically active matrices. The sensitivity to steering is for a standard sensor less than 2%, but significantly higher for low-range sensors. For ultra-low-range sensors which can detect H2S in the low nanomolar range, the steering sensitivity is more than 20%. The sensitivity to steering is defined as the difference between the signal in stirred and stagnant sample with the same sulfide concentration. This is exemplified here where a sensor measures in a continuously mixed sample. When the steering stopped, the signal decreases about 1%, which is typical for a sulfide sensor, and when the steering is reactivated, the signal is back to the original level. The lifetime is long if they are not physically damaged. Sulf sensors can last for years and measure continuously. The signal generated is so small that the electrolyte and reference capacity will never end out. Thus, the lifetime is not influenced by how much it is used. The signal stability increases with time. The diffusion coefficients through membrane and electrolyte settles over time, and as the lifetime is very long, the drift after some time is minimal. As the sensors are handmade, the drift vary among the sulfide sensors. Exemplified here with 3 sulf sensors starting with the same sensitivity, but after some time the signals are different. Thus, it cannot be predicted precisely how much drift a user will experience. We recommend calibrating whenever possible and convenient for all important measurements. The baseline does not change significantly with time. Physical impact on the sensor can, besides destroying the sensor, change the sensitivity and thereby the calibration of a sulfide sensor. The working electrode connects to the amperemeter via a thin, flexible glass-covered platinum wire. Physical impact, which shocks the internal components, can induce a displacement of the working electrode position relative to the membrane, thereby changing the sensitivity. Typically, such impact will induce a sudden signal peak followed by a stabilization time, but the sensitivity might not return to the original sensitivity caused by a displacement of the working electrode position. SOLF sensors stand up to 5 times atmospheric pressure without being pressure compensated. However, as other Unisense microsensors and electrodes, we can pressure compensate the inner parts of the sensor so they do withstand full oceanic pressure. When pressure compensated, they are tested to be able to withstand 600 bars. Ultra-low range sensors do not stand pressure without being pressure compensated due to the white membrane. This photo shows a SOLF sensor mounted in a Unisense in situ amplifier where an oil-filled membrane equilibrates in situ pressure with the sensor electrolyte. In the web lecture about amperemetric microsensors, the temperature influence is discussed in detail, and it is explained why temperature compensation is difficult for amperemetric microsensors. The temperature interference is about 2% per degree C. For sensors used with a new Uniamp portfolio, temperature is compensated for within a plus/minus 3 degrees Celsius interval. We therefore recommend calibrating SOLF sensors and measure at the same or almost the same temperature. The sensors can be used from -10 to 60 degrees Celsius. At higher temperatures, the baseline and noise level increases and compromise the sensitivity. I will not in this presentation go into details with all the adaptations and modifications we do to the SOLF sensors. This is covered in the quick guide, but I would at this point describe how a needle-embedded sensor is made. We make needle-embedded versions of the SOLF sensors in order to give some protection to the sensor tip from being damaged. We make them in 2 different versions, SOLF-N and SOLF-NP. The latter is made for piercing membranes. This is a schematic drawing of the tip of a SOLF-N and SOLF-NP sensor. The needle protects to some extent the glass, but the sensor tip is still fully exposed to the sample solution. The needle and the glass part of the sensor is glued together inside the needle, so no sample liquid will intrude into the needle. This would otherwise cause a huge carryover effect. I will now turn to troubleshooting SOLF microsensors which do not exhibit normal performance. Naturally, small glass tip sensors are fragile, and the tip might break if it hits something hard. This is a photo of an intact SOLF-10 sensor, and to the right a photo of the same sensor is shown, but now with a broken tip. It is seen how the working electrode is exposed as the glass tip is missing. A broken sensor will in water give very high signal, typically out of range, as the working electrode is now directly exposed. So if the tip breaks during measurements, a sharp signal rise will occur to the out of range level. Sometimes the sensor does still respond to sulfide, because the exposed working electrode can still reduce sulfide, but it will be very unstable. It is not possible to repair a broken sensor. If the sensor tip gets biofouled or covered with sticky polymers, it might measure incorrectly. The sensor tip tolerates almost all possible cleaning substances like alcohols, acids, detergents, proteinase solutions, etc. So it is recommended to insert the sensor in different cleaning solutions to see if it solves the problem as the first attempt to remove the fouling. If chemical cleaning does not remove the fouling and restore normal performance of the sensor, a physical cleaning is the only solution. For SOLF-50 and larger sensors, it is safe to wipe the tip with a piece of soft wetted fabric or paper. If you hold the sensor so the tip points away from you, the wipe direction must always be the direction the tip points, never against the tip, which will impose a risk of tip damage. For SOLF-25 and SOLF-10 sensors, physical wiping might break the tip. For physical cleaning of these fragile sensors, we recommend that you hook the sensor up in a microprofiling system and gently insert the sensor into a soft matrix which gives some shear force on the fouling material and removes it. The best material we know of to do this is Oasis flour foam. It should be wetted before inserting the electrode. For customers using a 3 to 5 micrometer sensor, we recommend to profile in an agar or agarose gel to remove the fouling. These curves illustrate a normal start-up behavior of a SOLF microsensor when connected to a Unisense amplifier and polarized. The signal is high and downwards drifting right after polarization due to unspecific reaction on the working electrode. If there is not such initial peak signal, but instead the signal does not rise much from zero, it might be due to a gas bubble stuck in the tip which disconnect the working electrode from the reference. There must be an air/gas phase in the electrolyte cavity in order to make room for temperature-induced expansion of the electrolyte. And if the sensor package is turned upside down during shipment, a gas bubble can be trapped in the tip. Such air bubble can be removed by shaking the sensor like it is demonstrated here. The bubble will become loose and rise to the top of the electrolyte cavity, and connections will be restored. In rare cases, a gas phase can develop in the tip at the position of the working electrode, and such gas cannot be removed by shaking. So if there is no signal from the sensor, this could potentially be an explanation. Such gas phase can easily be removed by inserting the tip into degassed water, which will drag the gas out of the tip through the membrane. Fill water into a glass bottle and boil the water. This drags gases out of the water. Let the water cool to room temperature or below without shaking the bottle or mixing the water. Place the sensor tip into the water for some hours. The gas phase will be removed by this procedure. If a sensor experiences a physical impact, like a drop on the table, the working electrode could be displaced. If the displacement results in a working electrode retraction from the silicon membrane, the signal will be slow and the sensor will still work but have lost its original behavior. It is unfortunately not possible to restore original performance. A physical impact like a drop could also damage the glass insulation on the platinum wire connecting to the working electrode. This will typically result in an elevated and noisy baseline signal due to exposure of polarized platinum to the electrolyte. Chemical reactions taking place on the exposed platinum surface will create a current which will overlie the working electrode generated current. The size of the baseline increase will depend on the degree of damage to the platinum wire insulation. Such damage cannot be repaired. For fast-responding SOLF sensors have a very short membrane, which can be vulnerable to electrostatic discharges. A charged person who touches, for example, a beaker in which the sensor tip is placed, can induce a potential difference of thousands of volts across the membrane and potentially induce a discharge which destroys the membrane. To be sure that this does not happen, a grounding wire should be connected to the liquid or setup in which the sensor tip is placed to the ground socket of the Unisense amplifier. Standard sensors are not vulnerable to electrostatic discharges. A sensor with a damaged tip membrane will have a very unstable signal, strongly affected by electrical noise. By grounding the sample or experiment to the ground socket of the amplifier, the signal will stabilize. A damaged membrane cannot be repaired. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.